Hi. Okay, so last section of the first chapter. So, of course, what we've done so far is we've talked about Turing machines, and we talked about them as a model of computation. So what we want to see today is a different model of computation, recursive functions. It has two advantages. The first is that there will be some features that we're going to find convenient for later, and since it's not later, I can't really explain them at great length to you. I'll talk about them a little bit at the end. The second advantage is that it's sort of a contrast with Turing machines. I mean, these are very different than Turing machines. They have a very different feel. So if I showed you another machine model that was a little different, you'd say, okay, I can see that you could have different machine models, but this is a very different, sort of more mathematical feeling model. And so a person walks away from it thinking, so you can do many quite different things. And that makes Church's thesis the contention that no matter what of many different approaches people have taken, it always proves to compute the same things. That makes that contention a little more persuasive. Okay, so let's start in. So let's see, here we are. I'm talking about primitive recursive functions, and then we're going to talk about general recursive functions. So the word primitive suggests that there's going to turn out to be something a little subtle, but something that is lacking in this particular collection of functions. And that's true. Okay, so let's start in. So grade school students, of course, learn addition and multiplication by some mildly complicated algorithms. You know, you have to multiply by carrying the one, this kind of stuff. Grossman produced a more elegant definition. Here's the formula for addition. So I'm going to call addition the function plus. Plus takes in as input two different natural numbers. Takes in as input two different natural numbers, and as output gives a single natural number. And Grossman defines it this way: that the plus of xy is x anytime y is equal to 0, and the plus of xy is the successor, s is the successor function, the plus 1 function, what in C you call plus plus, the successor of the plus of x and z, where y is the successor of z. This is one of those things where you need an example, and then having seen the example, the definition is perfectly clear, so let's look at the example. Here is the plus of 3 and 2, okay? The definition says, because this says 2, not 0, so the definition says it's the successor of the plus of 3 and 1. And let's see, the 3 and 1 is 4, the successor of that is 5, so that's right, okay. Well, plus is defined as the successor of the plus of 3 and 0. So that's what recursion is about. We go back to the well here a second time. The successor of the plus of 3 and 0. And of course the plus of 3 and 0, the definition says, is 3. Right up there it says 3. The plus of 3 and 0 is 3. So this is the successor of 3, which is 5. Now you said, well, how do we know? Well, the answer is, of course, that successor is an already defined function. So using successor, we can define plus in a very elegant way. You don't have to do something like you learned in grade school where you have to carry, none of that stuff. Instead, you just simply do this very straightforward recursion. Now, multiplication has the same form. Here's the product. Here's the product operation. It says product of x and y is equal to 0 if y is 0, and the plus of the product of x, z, and x. So product depends on plus. And just to go through the calculation here, the product of 2 and 3, the product of 2 and 3 is the plus of the product of 2 and 2, and also 2. See that? 2 right there. Okay? Well, we've seen this once, so you have some idea that I'm going to expand product of 2 and 2. And indeed I do. The product of 2 and 2 is the plus of the product of 2 and 1 and a 2. Okay? Well, now we know the game. I'm going to expand product of 2 and 1. So we do. The product of 2 and 1 is the product of 2 and 0. Is the plus of the product of 2 and 0 and a 2. So that is to say, lest the person lose track here, this plus right here, that part right there, is the expansion of this part right here. Okay, very computer-like, isn't it? Yeah. Okay, but now we've gotten to the point where the operation, where all this fooling around stops, because the product of 2 and 0 is 0. Just by the first line of the definition, product of 2 and 0 is 0. So now we're looking at the plus of the plus of the plus of 0 and 2. And we did the plus of on the last slide. That's going to be 2, comma 2, comma 2. So this, in short, is the plus of 3 2's, and so that gives you 6, and that was the right answer. So this basically, this definition right here turns product into repeated addition, repeated plussing. This definition turns product into repeated plussing in a particularly elegant and nice way. Isn't that nice? It's mathematically sweet. Okay, so next up, we did addition, we did multiplication. We must be going to do exponentiation next. So here we are with exponentiation. We're looking for the product of x and y, and it's going to be, the power of x and y, and it's going to be the product of the power of xz comma x. In short, if you want to take the, for example, 7 to the 2 power, then that's going to be the product of 7 and 7. If you want to take 7 to the 3 power, that's going to be the product of 7 and 7 to the 2. If you want to take 7 to the 4, that's going to be the product of 7, there it is, 7, and 7 to the 3, kind of thing. And of course, we'll do a little pencil and paper example here if I can manipulate what I need to manipulate. Let's see here, take out my paper. There we go. Hide this, hide that thing. Oh, there's my paper. It's a little sideways. Something's in the way on my desk. There we go. Okay, so I'm going to do the power of 2 and 3. Power of 2 and 3. And I don't have the definition right here. You have the definitions on the screen, but I think it's not bad. A person can figure out what this is going to be. So that's going to be the product of the power of 2 and 1. Oh, sorry, of 2 and 2. And do you mind, I know it's obnoxious, but I'm going to leave it a lot of space, and comma 2. And boy, this focus is really starting to annoy me. Okay, so I got to expand power. Okay, so product of power expands to remember the product of the power of 2 and 1. Don't forget this comma 2 over here. Power of 2 and 1, comma 2. I know the spacing is a little obnoxious, but there we go. Okay, so this is going to be the product of, and power of 2 and 1 expands to become the product of the power of 2 and 0. Don't forget this comma 2. Don't forget this comma 2. And now over here is a comma 2. And now you see the game. Now you see what's happening here. The power of 2 and 0, 2 to the 0 is 1. Fill in the rest. I almost put an extra paren at the beginning. And when all the smoke clears here, we've got a product of 1 and 2. We just did product a few minutes ago, and I think agreed that it was correct. So the product of 1 and 2 is going to give you a 2. Product of that with 2 is going to give you a 4. Product of that with 2 is going to give you an 8. And of course, that's the correct answer. And in any way, it's a sensible thing because it's the product of the 3 2's. Okay, so power is the product of the product of the power of xz, where z is 1 less, and x. Okay, let me rearrange my desk here back to what I was supposed to be and move on to the next slide. Okay, so what we have then is we have an idea for what to do. A function is defined by primitive recursion from G and F if it has the form where oops, there we go. If it has the form where there's a line where the function on the top line is already previously defined, so we're able to use it to make new things. And the function on the bottom line, the h, is already previously defined, so we're able to use it to make new things. when you define h here, you're allowed to use prior values of f, and by prior value, I mean the relationship between y and z. That y is the successor of z, said in another way, z is 1 less than y. So you're allowed to use the prior value of f. You're allowed to use values of the input variables of the parameters x0 through xk minus 1, and you're also allowed to use z. So we can define new functions from old functions by this schema of primitive recursion. And the fact that addition and multiplication and exponentiation are all defined that way in an elegant fashion argues strongly that there's something to this. The bookkeeping is a little bit awkward when you go to do the homework problems. You find yourself sometimes saying, exactly how many x's are there supposed to be? So the bookkeeping is that the arity of f, the number of inputs, is one more than the arity of g. So you see, for example, that f takes x0 through xk minus 1, and g takes x0 through xk minus 1, but f also takes y. So f's got one more thing than g does, and f's got one fewer thing than h does as inputs. You often see people abbreviate in practice the x's as x bar, just to make it easier to write. So for example, we've just seen that plus is defined from g of x0 equals x0 and h of w x0z equals successor of w. Product is defined by g of x0 equals 0 and h of w x0z is equal to plus of w x0. It happens not to need the z. The power function is defined by g of x0 equals 1, and h of w x0z is the product of w and x0. And again, it happens not to need the z, even nobody made that a crime. Okay, so what we're seeing is that we're building up somehow bigger functions, more complicated functions, higher powerful functions, whatever that means, from smaller, more elementary, more primitive functions. Okay, in a recursive manner. So let's go and do a couple more, and of course there's plenty more in the homework. The predecessor function. So it takes you from 7 to 6, it takes you from 100 to 99, it takes you from 1,000 to 999. The predecessor function. That's a function. That's a person can ask, however, can you do that by this scheme that we've just introduced? Can you define predecessor using the scheme that we just introduced? And of course the answer is yes, otherwise it wouldn't say example. So the answer is yes. But the point is here, the thing that sometimes gives people trouble, we defined predecessor. Now our job is to make it fit the scheme that we were just given. Okay, so again, we defined predecessor, described predecessor, and now our job is to make a definition that has it fit the scheme we just gave. Okay, and it's not a hard job. Predecessor of y is equal to z. If y is a successor of z, and predecessor of y is equal to 0 if y is equal to 0. So the two legs here are 0 and successor. The arity bookkeeping works out. I'm not going to go through that. Subtraction is another example. We're going to define subtraction. That's defining a function. The next job, the job that you'll have in the homework, is to define it in a way that reflects the schema of primitive recursion. So you got to have two steps here. See how this doesn't have y equals 0, y equals successor up here where it says, where it gives the description of what is subtraction. It doesn't say y equals 0 and y is equal to successor. That's not the two cases. So we have to define subtraction. It's called proper subtraction because you have to be careful not to come up with negative numbers. We have to define subtraction in such a way that it's defined using these two cases. So that's what the homework is going to call for. In any event, it's not all that hard. Proper subtraction is x if y is equal to 0. I mean, what happens when you take x minus 0? It's x. Even if x is 0. Yeah, that's right. Okay, and otherwise, it's the predecessor of, remember we defined predecessor a minute ago, so we can legally use it now. It's the predecessor of the proper subtraction of x and z. So for example, if you wanted to take, say, x minus, let's take 100 minus 7. 100 minus 7 is you take 100 minus 6 and then take one more away. Again, 100 minus 7, 100 minus 7 is take 100 minus 6 and then take one more away. So again, not that hard. When you get used to these kind of things, at some point you start whipping them off because there's a certain pattern to them. You have to basically see how smaller things are built, how bigger things are built up from smaller things. So what we get then is the collection of primitive recursive functions consists of those that can be defined from the initial operations of the zero function, the zero function, the successor function, and the projection function. The projection function just takes its capital I sub I of x0 through xn minus 1 is equal to x sub I. So the I here and the I here are the same I. That's a capital I because this is an extension of the identity function. That's the reason why that's a capital I. So these are three very simple functions, and you use them to start. And then what can you build if you follow this? Procedure of using a function composition and also this new procedure of primitive recursion. And just a comment about function composition. Function composition doesn't just cover the simple case of f circle g of x is f of g of x. It also covers the case of simultaneous substitution, so that you have, if you have f of x0 through xn, and you have an h all the way up through hn, h naught through all the way up to hn, you're allowed to substitute them all at once. Okay, so you're in fact substituting n plus 1 many things in this. So it's not just a question of substituting one thing, it's a question of substituting all these things. So that composition covers sort of multiple simultaneous composition. Okay, in any event, the point is that we arrive at some collection of functions. And why are we talking about this? How did we go from Turing machines to this? And the answer is the collection of primitive recursive functions is very large. It includes addition, proper subtraction that we just did a minute ago, multiplication, integer division, exponentiation, the equality, remainder, sum of a bounded number of terms, product of a bounded number of terms, and just about every function that comes to mind. Just about every function that comes to mind. Just about. So a person can ask, is this the same collection as the collection of things that you can compute? Does Church's thesis apply here? Is this the collection of things that are computable by a Turing machine? Is this the collection of discrete and deterministically computable things? And the answer proves to be no. It's a little tricky, but the answer proves to be no. So to show you that the answer is no, I got to show you a function that cannot be computed by the scheme we just talked about. And here's the function. It's Ackermann's function. Ackermann's function is, you say to yourself, let's look at the definition of plus, let's look at the definition of times, and let's look at the definition of exponentiation. So we call this the plus operation, we call this the product operation, we call this the power operation. Look, there's a pattern. The plus operation is you take successor and iterate it y many times. The product operation is you take plus and iterate it y many times. The exponentiation operation is you take product and you iterate it y many times. I mean, that's a pattern. Okay, so what does a person do next, you think? Well, surely it's clear that you're going to iterate exponentiation y many times, and etc. Okay, so, and the person who first discovered this, person who first thought about this, Dedekind, was very excited. He thought he had invented the first genuinely new mathematical, operation in centuries. So I wrote it out in a way that makes it especially clear. Look at what happens in the bottom line here, the bottom line here, and the bottom line here. H1 is H0 of x comma H1. H2 is H1 of x comma H2. H3 is H2 of x comma H3. So that's the pattern. You might call this the level 1 function. Then this is the level 2 function, and this is the level 3 function, and then it's pretty clear what to do for the level 4 function, and the level 5 function, and the level 6 function, and et cetera, et cetera, et cetera. So what we're doing then is we're building up a collection of things that are in some sense natural, because they come right from plus, product, and power. Okay. So that's the so-called hyperoperation. Hyperoperation, which is why I used a capital H for it. What to do in the initial case, what do you do if y equals 0 is not perfectly clear, it's a little bit awkward, a little bit messy, and it's possible to make it a little cleaner, but I left it the way it is. because I like the connection with plus, product, and power. This line here is perfectly clear what to do. Is that you take, to get h of level n, to get the level nh, you take the level n minus 1h, x, and the level nh. To get the level nh, for example, the level 3h, you would take h of 2, comma, x, comma, h of 2, comma. And then you go through the lemma here. It says that indeed that h of 0 is successor, h sub 1 is plus, h sub 2 is product, h sub 3 is power. And I'm not going to talk those through, but they're pretty clear. Prove them by induction on y kind of stuff. And the theorem down at the bottom here is that the hyperoperation is not primitive recursive. Was shown by Hilbert's student Ackermann. You remember Ackermann from the Entscheidungsproblem? Same Ackermann. The hyperoperation is not primitive recursive. It has the property that the level 3h is primitive recursive, the level 4h is primitive recursive, the level 5h is primitive recursive. It can be made according to that scheme that we talked about. Any level k, h, is primitive recursive. But you cannot compute them all at once. H, where n is a variable instead of a parameter, is not primitive recursive. So that's awfully interesting. Okay, well then we've got something that we think is computable, because you could take out a pencil and paper and do the darn thing. You could write a program to compute that thing that I just had on the prior slide. So we said, well, there's something that can't be computed in a primitive recursive way. That's true. So what do we have to add to primitive recursion so that we can get everything you can do with a Turing machine, so that we can get everything that a discrete and deterministic device can do, so that we can get everything that is intuitively computable? What do we have to add? And the answer is this. We have to add basically unbounded search. So suppose you have a function that's total, so that for every input n tuple there's a defined output number. Then f, you notice this says n and that says n plus 1. Then f, defined from G by minimization, or what's called mu recursion. You write f of x bar is the least y, that's a Greek letter mu, the least y, where G of x bar y is equal to 0. The function is defined by finding the least y so that G returns a 0. It is defined by primitive recursion from G. That's unbounded search. So what we have in mind is that you are looking for, we try y equals 0, plug it into G, does it work? We try y equals 1, plug it into G, does it work? We try y equals 2, plug it into G, does it work? We try y equals 3, etc., until we find a y that works. That's unbounded search. And an example says more than any number of definitions. So a number n is called a Carmichael number if, for all b's between 1 and n, relatively prime to n, the number b to the n minus 1 leaves a remainder of 1 on division by n. And it's important for a number theory purposes, but for our purposes, we just want an example of something that you can compute. If you give me a b, I can figure out whether it's a Carmichael number because I plug in. If you give me an n, I can figure out whether it's a Carmichael number because I plug in all these b's. I figure out whether they're relatively prime to n, and then I compute b to the n minus 1 and take the remainder. So it's either a Carmichael number or it isn't. That is to say, this function right down here is computable, and in fact, it's primitive recursive. This function down here that simply follows the first sentence is primitive recursive. So I want to be able to compute where C of n is the nth Carmichael number, and so I defined to find, once you've found C of 12, how do you find C of 13? Well, you look for the least y that has the property of, oh, that says capital F, that's supposed to say capital C. I apologize. It's supposed to be capital C. Typo. You find the least y greater than C of n minus 1 with the property that it's a Carmichael number. Okay, so unbounded search. We don't know of a formula to compute Carmichael numbers, so that's no problem. Just put it in a computer and start looking for the next one. Unbounded search. That's what's missing from primitive recursion. You can't do unbounded search. But you could on a Turing machine, you could on a discrete and deterministic device, you could on your laptop do unbounded search. So that's what's missing from primitive recursion. Once you add unbounded search, you get what's called general recursive function, partial recursive function, mu recursive functions, or just plain recursive functions. So we say a function is general recursive if it can be derived from the same initial operations as primitive recursive, the zero function, the successor function, and the projection functions, by a finite number of applications of function composition, primitive recursion, and minimization. The minimization, of course, is the new one, and it proves to be the case that the collection of general recursive functions is the same as the collection of functions computed by some Turing machine. That is to say, this is an alternative approach to defining computability. So it has the advantage that it's obviously very, very different than the approach I showed you in the first video of defining a Turing machine a device. This is very, very different. When people take very different approaches and come to the same answer, you start thinking that maybe the answer is right. So that's one of the ways in which Church's thesis is made strong. Now this development, the development of computable functions, has the advantage that we go straight to functions. We don't have to define, on a Turing machine, you have to say, well, we'll take all these ones to represent some integer, and then you'll look at the prime factorization of that integer, 2 to the a, 3 to the b, and then we'll take the power, a to the b. None of that nonsense. You just simply compute exponentiation right off. So it's very straightforward here, what you mean by the functions that are computable. It's exactly this collection of functions. It, however, has the disadvantage, this approach to the definition of what's computable, has the disadvantage that it isn't obvious. It's not obvious that this is what's computable. You kind of go through and you'd say, well, you could compute the successor function, you could compute the projection function, and then given a bunch of functions, you can compute the composition, so that's all right. So I can see that all of these are computable, but it's not clear to me that if it's computable, it's one of these. So Turing machines has the advantage of making clear, of clarity, of making clear that this is what you can do with a device, but Turing machines has a disadvantage of this ugly representation stuff. In any event, we're going to need general recursive functions from time to time as we move through the course, so they have their own, they are on a standalone purpose. But in this chapter, one role that they play is giving an alternate definition of what is computable, because a person says to themselves something like, what do you mean by other people came up with other definitions? Well, this is an example of another definition, not at all like Turing machines, and it collects the same functions. You put them all in a big pile, it proves to be the same as Turing's pile. You start saying to yourself, maybe that's the right pile. Okay, all right, very good.